object experiencing motion on an inclined plane again. In order to build our free body diagram, I'm first going to place the object at the top of that inclined plane so that way I have more real estate to work with in this problem. Though it may not reach the top of that inclined plane, all vectors hold true throughout the object's motion. First, I have my force of gravity, which is equal to 3.5 newtons. My normal force and my force of gravity applied down the inclined plane. Solving for those using appropriate trigonometry, remember we can use whichever reference angle we wish. 25 degrees holds true for here, but 65 degrees holds true for up here. You can use whichever angle you wish as your reference angle. I would, in this situation, use 65 degrees as my reference angle. Normal force is equal to force of gravity times sine 65. This is the opposite end of the triangle with regards to the 65 degrees. Solves for normal force. That applies for this vector here. That vector can be moved and transposed over there, demonstrated perpendicular to the inclined plane. Force of gravity applied down the inclined plane. In that case, that's going to be equal to 1.48. Excellent. It appears that we're almost done with our free body diagram. We have one other force to deal with, and that's the force of friction. The difficulty comes from which way is force of friction traveling? Is it helping us move up the inclined plane, or is it impeding our motion? Which way is force of friction going? In this case, we know that it's actually impeding our motion and working against us. We know this because force of friction always opposes whichever your intended or directed motion is. Because this ball is traveling up the inclined plane, our force of friction must be working down the inclined plane. That's not anything that we can memorize. That's very situation specific. That's something that we come up with logically, thinking up the problem. In this case, we can solve for the force of friction mathematically by remembering that force of friction is equal to normal force times coefficient of kinetic friction. In this particular case, our force of normal, our coefficient of kinetic friction. Now, this is a rotating object. This is a ball that's traveling up an inclined plane. We'll learn in Unit 8, while some of the physics here is pretty simplified and honestly kind of bogus. But we can worry about that in Unit 8. Right now, we're going to land on a force of friction value there of 0.951 newtons. 0.951 newtons. When you look at everything that's going on in this problem, once again, the only forces that we really sum up when solving for the net force are the forces that are acting parallel to this inclined plane. That would be our force of friction and our F gap. I wouldn't totally demolish and get rid of forces of gravity, normal force, but when solving for the net force in the situation, it's only the forces that are acting parallel in the system that we factor. In this case, logically, because we have force of gravity and force of friction working in conjunction with one another, our net force is equal to force of friction plus force of gravity applied down the inclined plane. Those are the only two forces at work. The fact that we kick the ball up the inclined plane has nothing really to do with summing up our net force because we're not constantly dribbling the ball up the inclined plane. There's no rope tied to the ball that's pulling it upward constantly. There's no constant upward force. The net force is therefore exerted in the opposite direction of our intended motion. Net force in this case being equal to 2.43 newtons. Returning to the original question, how far does the ball travel up the inclined plane? We can now solve for that by grabbing an acceleration. We can grab an acceleration value by saying the net force, which we now know, is equal to the mass of this object times our net acceleration. In this case, we have a net force, a mass, times net acceleration. Net acceleration is equal to 6.94 meters per second squared. I'm going to add something to that. I'm going to say that that's negative. The reason why I'm going to stress that is that the net acceleration is against our directed motion. It is against our initial velocity. Therefore, when we plug it in appropriately kinematically, we need to account for the fact that that acceleration is negative. The forces of friction and the forces of gravity applied down the inclined plane are slowing this object as it travels upward. Our known initial velocity is 15. Our known final velocity is 0 because this object will come to rest at some point traveling up the inclined plane. The question was asking for d. What's your distance traveled? The best equation to use in order to solve for that is vf squared is equal to vi squared plus 2ad. Plugging in. And solving.